Hello dear students, in this lecture we will try to understand what coronal mass ejections and solar flares are. In continuation to our discussion on sunspots, solar activity, we have identified what are the active regions and how the sunspots become low temperature regions with a very strong magnetic field due to the differential rotation of the sun. Okay, right. Now, first topic is the coronal mass ejections, which are called as CMEs, coronal mass ejections. So, the image that you see, a graphic that you see on the left, clearly shows massive outbursts of plasma into the interplanetary space. So, this region of which just vanished towards the outer regions of the solar system are these are called as the coronal mass ejections. So, they are very energetic bursts of plasma. Okay, so the coronal mass ejections are huge bubbles of gas or huge bubbles of energetic plasma threaded with magnetic field lines ejected from the sun over several hours. So, the coronal mass ejections are simply those events during which bursts of plasma are thrown into the interplanetary space, and this event can last several hours. This process of throwing away large masses of gas can occur over several hours. All right. So, some other important features of these coronal mass ejections, they are large eruptions of coronal plasma. They originate from active regions in the sun associated with a solar flare. So, you see that solar flares and coronal mass ejections are interconnected. The burst and the flash that you see, okay, they are very frequent during a solar maximum and they are not so frequent during a solar minimum. Typically, during the periods of solar minimum, approximately one coronal mass ejection may occur per week, and during solar maximum, from the active regions, you can expect up to 2 to 3 coronal mass ejections per day. Not all these coronal mass ejections are directed towards the Earth. Sometimes we see them, sometimes we don't. Okay, right. Now these are the basic characteristics of coronal mass ejections. So you can expect during the periods of solar maximum up to 2 to 3 events per day itself, okay, which is very large in comparison to what you can expect during solar minimum, right? So coronal mass ejections are large eruptions of coronal plasma that originate from active regions on the sun and are carried by the solar wind. Okay, there can also be some interaction with the solar wind. That's a different topic. So typically, the coronal mass ejection has three-part structure, which consists of one, a cavity of low electron density. Number two, a dense core, and dense core, which is actually the prominence, which appears as a bright region on the coronagraph images. What are coronagraph images? It is an instrument on a satellite or anything which is observing a star or sun. What is done is you put a disk and cover the visible or the brightest part of the sun, and then you get to see the expanding gas or the solar wind or the coronal mass ejection or any fluid that is trying to escape the star, right? So it is similar to the total solar eclipse when the moon near the totality, when the moon completely covers the visible disk, then you get to see the coronal uh, ejection or corona flowing away from the sun, or the solar wind flowing away from the sun, right? So typically you have these three parts: one, a cavity of low electron density, then you have a dense core, which is basically the mass that is escaping from the sun, and third, most importantly, a bright leading edge. And many CMEs are missing one of these elements or even all of them. Okay. So most CMEs originate from grouping of sunspots that are associated with frequent solar flares. So it is evident that coronal mass ejections originate at the sunspots. Like I said, they are the windows of these all the solar prominences. So these regions have closed magnetic field lines where the magnetic field strength is large enough to contain a lot of plasma. And when this is heated and then if it is thrown into the space, that is what you get to see as a CME. When a CME occurs, these field lines are opened so that the energy that is contained can at least partially escape from the sun. Okay, so this trapping of charged particles by the magnetic flux lines, when this breaks, plasma will escape. The shock front, which is at the leading edge ahead of the CME, and this is also important for interaction with the Earth's magnetosphere. So this is the interaction we will talk about. So this leading edge or the shock front is very important when it interacts with the Earth's magnetic field or the Earth's magnetosphere itself. Right. So this is the basic definition or some very basic properties of coronal mass ejections. Right. And for example, the rate and location of CMEs vary with the sunspot cycle. What does it mean? Sunspot cycle varies from maximum to minimum. The rate, the number of ejections that can happen over a particular day or a week, and the location from where these ejections are originating vary as a function of the sunspot cycle. So if you are during the maximum, it is more likely to be this. During the minimum, it is more likely to be something else. Okay. So during solar minimum, just like we have seen, one ejection per week in the coronal streamer belt near the solar magnetic equator is expected. And during solar maximum, during active periods, you can expect 2 to 3 ejections per day from the active regions whose latitudinal distribution is more homogeneous. Okay. So spread is of velocities, let's say, it can vary anywhere between 20 kilometers per second to 2,700 kilometers per second. So imagine particles with mass traveling at 2,700 kilometers per second is intense or is extremely energetic. Okay, so with an average speed based on the measurements of Soho Lasco, it can vary anywhere between let's say 480 to 700 kilometers per second, and the average mass of one coronal mass ejection or the bubble of plasma is of the order of 1.6 10 to the power of 15 grams. Okay, and magnetic field associated with the plasma, like we have already seen, it follows what is called as a frozen in condition. The magnetic field often is very complex. Okay, and this is also important for the interaction of the coronal mass ejection with the Earth's magnetic field. Okay, the way it interacts. This interaction will lead to many possibilities of entry of plasma into the geospace. Okay. Then the second most important solar prominence is the solar flare. Solar flare, what is solar flare? Solar flare is a violent explosion in the sun's atmosphere. You see this image on the right. You see a bright intensity appearing in the southern hemisphere in the mid latitudes of the sun. This explosion or this bright intensity, bright light is basically referred to as solar flares. So solar flare spans electromagnetic frequencies from radio to X-ray. So all the wavelengths are illuminated at once. Okay. So this may be caused by the release of energy stored in the twisted magnetic field lines, and large increase in X-ray flux can affect satellites. Of course, that becomes the space weather effect itself. Okay, energy release accelerates protons in the solar wind and cause disturbances in the Earth's magnetic field. Okay, so this is the spectral intensities that we have seen in the very early stages of this course. The amount of energy bundled into each of the wavelengths. Okay, that is the intensity that I'm talking about. It will increase enormously. So this image is taken by the GOES 13 satellite. Okay, which shows an intense X9 flare. X9 is the class of the flare. Depending on the strength of the flare, we have several classes. Okay, several classes which simply indicate the magnitude of the energy output or the flash. Okay, X-ray flash flare taken from the GOES 13 satellite. The flare was actually intense enough to damage the imager. The very imager that has taken the image, of course, it was damaged due to the intensity of the flare. This occurred in 2006, December 5th. Okay, so the solar flare is a violent explosion in a star's atmosphere, releasing up to the total energy of 6 × 10⁻25 joules. So solar flares take place in the solar corona and chromosphere. Okay, so heating plasma to tens of millions of Kelvin and accelerating electrons, protons, and heavier ions to the near speed of light. So they produce electromagnetic radiation across the electromagnetic spectrum at all wavelengths, from long wave radiation to radio, to the shortest wavelengths, let's say, for example, gamma radiation. Most flares occur in the active regions around the sunspots, where intense magnetic field emerge from the sun's surface into the corona. Flares are also powered by the sudden means the time scales varying from few minutes to tens of minutes release of magnetic energy stored in the corona. Okay, let us look at that once again. Flares are powered by the sudden release of magnetic energy stored in the corona. Okay, they can also lead towards the solar flares. So X-rays and ultraviolet radiation emitted by solar flares can affect the Earth's ionosphere and disrupt long-range radio wave communications. Of course, because if you expect an increased ultraviolet radiation input into the Earth's ionosphere, the ionosphere will act in such a way. Of course, ionospheric electron densities will increase because more photoionization is happening. As a result, the density maximums of the ionosphere can vary in height, and the typical time of travel of this signal will be affected, and many things associated with this can also change. So direct radio emissions from the decimetric wavelengths may disturb operations of radars and other devices operating at these frequencies. Okay, so this is something about the solar flares. Right. So this is something that we already discussed. The solar cycle contains this solar maximum and minimum. Minimum is the time of lowest solar activity, and it's rare to see sunspots on the sun during solar minimum. Okay, this is an image of solar minimum, which is again a blacked out central region of the star. What you see here is more or less uniform, but during solar maximum, these visible features you are able to see very clearly, right? So solar maximum, everything else is of course already discussed. Peak in solar activity, sunspots visible almost all the time. Now, more importantly, this can have more than 100 sunspots and some as big as 50,000 kilometers in diameter. So imagine 50,000 kilometers, the scale of 50,000 kilometers in comparison to the scale of the Earth. Right? So some sunspots may be as big as 50,000 kilometers in diameter. Okay, right. So more solar activity means increased number of sunspots. You will have more number of sunspots. You see here, leading sunspot, they always appear in groups, or they always appear in pairs. So more solar activity means increased number of sunspots, because more solar activity means actually involves more solar flares, right? So this is an image of solar flare which is zoomed out to be this. So you see so much of intensity coming from the sun, or so much of intensity, all the wavelengths, different wavelengths, their radiances are peaked during the solar flare. Okay, so on the sun's surface, solar flares are huge magnetic loops called prominences. When they touch, they short circuit each other, setting off huge explosions or solar flares. So they occur on the sun's surface, and they are found on lines dividing areas of oppositely charged magnetic fields. So more solar activity also means not only increased solar flares, more solar activity also means increased coronal mass ejection. This image that you see on the bottom right of the slide shows a beautiful coronal mass ejection leaving the sun, moving towards the outer solar system. Right. Now you can imagine the scale of the Earth to be just a dot in this image, and sometimes these coronal mass ejections can uh, directly impact the Earth's magnetosphere. Sometimes you may imagine that the Earth is somewhere else where the coronal mass, the path of the coronal mass ejection is not in line with the Earth. Sometimes it can happen, sometimes it may not. So this idea is called as the geoeffectiveness anyway. And more solar activity also means changes in the sun's magnetic field. So this image shows different polarities existing on the surface of the sun. And sun's magnetic field not only causes much of the solar activity during solar maximum, but also changes with the sunspot cycle. Okay, and the sunspot cycle is what the 11-year cycle that we are referring to. So every 11 years, the sun's magnetic field changes its direction. So 11 years, the northern pole will become the southern pole will become the North Pole, and the next 11 years, it will again reverse. So, for the North Pole to match the geographic North Pole, it will take 11 plus 11, 22 years. So, the full activity period, because within this, within this 11 years, you have one maxima, and let's say beginning with a minimum and then ending with a minimum. You will get one maxima ending with another minimum, right? So the total period of time is 22 years. So because suns rotates at different speeds, at the magnetic field of the sun gets twisted, right? That is pretty much known, and the sun's magnetic field gets twisted and wrapped like a rubber band. We have seen that. Observations from the Ulysses spacecraft show that during the reversal, the sun's magnetic field poles are located near the solar equator instead of the geographic poles. Okay. So the poles, like in the last lecture, I have shown a figure of a simulation showing how the magnetic poles will appear during reversal period. This observation by Ulysses actually matches that figure, the simulation actually. Right. Now, this is, in a sense, what we have discussed so far is this. One, in the beginning of the course, I have told that the solar terrestrial physics is basically a journey towards the Earth starting from the sun. We will try to understand what is sun, how the sun is able to generate so much energy, and how much energy are we actually talking about, and what are the different forms of this energy. When I say different forms of this energy, we not only receive energy in the form of light, we also receive energy in the form of plasma, energetic particles. And these energetic particle events are most dominant during a coronal mass ejection or a solar flare. Right? Now, this is one piece of the full picture which is concerned with the Earth. Now, what we are going to do is we are going to overlap this with the Earth system. Okay. So then we talk about Earth. It's the geospace surrounding the Earth, the magnetosphere, ionosphere, thermosphere, etc. And how this energy, when transferred to the Earth system, will influence or will affect physical processes. Let's say how the ionospheric chemistry changes or ionospheric conductivity changes, etc., etc. Right. Now, one missing information that we have at this point of time is a constant stream of particles escaping the sun's gravity and are actually creating this bubble of solar system in the interstellar medium. Right. So this stream of particles, or this constant fluid that is flowing away from the sun despite its tremendous gravitational pull, is called as the solar wind. Okay. So solar wind is constant. Coronal mass ejections, they are not constant. They are events. That means they occur and there is again a period where they don't occur. And the frequency with which these events occur seems to be directly dependent on the 11-year cycle or the number of sunspots, to be more precise. Now, most importantly, solar wind always interacts with the Earth's magnetic field, and we should be able to differentiate this interaction with the coronal mass ejection or the plasma interaction which happens during the coronal mass ejections. Right. Now, let us look at solar wind. Of course, before going there, a coronal mass ejection occurs, and typically 2 to 4 days later or 1 to 2 days later, sometimes if it is so energetic, we will receive this energy if the uh, trajectory of this coronal mass ejection, which is radially thrown out from the sun, which is rotating around itself. So there is a radial velocity which is associated with the solar wind, and at the same time, this velocity is may not always reach the Earth. So, for example, like I said, so if the coronal mass ejection or if the position of the sunspot is in phase with the revolution of the Earth around the sun, then there is a possibility that this coronal mass ejection, the huge bubble or huge cloud of plasma, may directly overlap on the Earth. When that happens, it can happen after a certain period of time, because we are talking about particles with mass traveling up to 500 kilometers per second. If it is light, if it is enhancement in the spectral UV spectrum or X-rays or visible anything, if it is enhancement in the spectral intensity, it will reach the Earth within 8 minutes, because it is electromagnetic waves. This energy is carried by the electromagnetic waves. Right. Now, solar wind is the most important piece of information to understand sun and earth coupling, how the sun influences so many things on the earth, in the Earth's atmosphere, etc., in the exosphere, etc., in the magnetosphere, etc. So, solar wind is basically an extension of solar corona to very large heliocentric distances. So, what is solar wind? Solar wind is just a stream of particles which is going away. So, a very easy example is if you are boiling a pot of water, and then you will see that on the top a vapor escaping from the water surface is like the solar wind escaping from the sun. So, it is constant. Solar wind is ionized gas emitted from the sun, flowing radially outwards through the solar system and into the interstellar space. So, solar wind is actually the reason for the creation of this bubble, which we call as the solar system. So, the edges of solar system are governed by the extent to which solar wind is able to push the interstellar plasma outwards. So, this being a fluid, this exerts some pressure, of course. Whenever this pressure is equal to the interstellar pressure, medium pressure, we form a boundary which we call as the solar system. Right. So, solar wind is a very important piece of information for understanding this whole system. So, Earth's atmosphere is stationary. The sun's atmosphere is not stable, but is blown out into the space as the solar wind, filling the entire solar system, and then some more. So, the first direct measurements of solar wind were in the year 1960s, but it had already been suggested that there is solar wind, constant solar wind in the 1900s. So, people earlier thought that solar wind is not a constant process. Rather, whenever coronal mass ejections happen or when there are a lot of solar sunspots, people thought solar wind can reach only during that periods of time. So, to explain a correlation between the aurora and the sunspots, Birkeland suggested that there is a continuous particle stream of particles from the sunspots. Okay, because whenever there were auroral observations in the northern Europe or in the high latitudes, they're always accompanied with larger number of sunspots on the sun. So people thought plasma is emanating from the sunspots and then it is reaching the earth. That's why it is able to create the auroras. But there were other suggestions that particles were emitted from the sun only during the flares and that otherwise space was empty. Chapman and Ferraro in 1931 proposed that the solar wind particles emanate only during the flare events and otherwise space was empty. Right. So observations of comet tails ultimately led to the suggestion of continuous solar wind. Comet tails are formed because of the interaction of solar wind with the comet surface, so which evaporates the let's say liquid, the solid water, frozen water on the comets, which eventually forms this tail. Now, the direction in which comet tails were pointing were always in radially outwards from the sun, whether the comet is traveling radially away or radially towards. So, this suggested that something is moving away from the sun, a fluid is moving away from the sun, and this is making the tail appear to be aligned in the opposite direction. Okay. So, the question of continuous solar wind was resolved in 1962 when the Mariner 2 observations returned nearly 3 months of continuous solar wind data while traveling to Venus. Okay. Right. So, this is just an image. Comet tails point directly away from the sun regardless of comet's velocity, whether it was inward or outward. Just two cases out of all the possibilities. Whether it was inward or outward, the tail seems to be pointing away from the sun. What should be this? This must be ionized gas pushed away by the ionized solar wind. Okay, this is reading this again. So this must be ionized gas pushed away by solar ionized gas, which is called as solar wind. So solar ionized gas means there can be He2 plus or H plus or electrons, etc. So these particles, these energetic particles, are responsible for pushing the gas away from the sun. Right? So by studying the tails of the comets, scientists determined that there must be a radiation pressure and solar wind pushing out from the sun because the tails always head away from the sun. Okay, so this is an image of the comet Hale-Bopp, which was taken when it was visible or in the closest proximity to the Earth. Right. And these are the measurements of solar wind by Mariner 2 in 1962 on the way to Venus. So what do they suggest that there is a constant stream of particles, protons per centimeter cube, for nearly September to December, for nearly 4 months. 3 to 4 months of observations suggested that there is a continuous, there is a non-zero particle flux in the space, which must be solar wind itself. Right. Now, what and all constitute the solar wind? The most detailed observations of the solar wind have been made from the spacecraft near the Earth. So, these are the properties which are observed near the orbit of the Earth, of the solar wind. So, typically protons 6.6 per centimeter cube, which is a very good number. Okay. And electrons, 7 electrons per centimeter cube, He2 plus doubly ionized helium, 0.25. Flow speed, nearly, the radial speed is of the order of 450 kilometers per second. And proton temperature, 1.2 10 to the power of 5 Kelvin. Electron temperature being different, 1.4 10 to the power of 5 Kelvin. And the magnetic field nearly of the order of 7 nanotesla. So these properties change continuously, but these are the average parameters which are observed near the Earth's orbit. And more importantly, if you read about the recent Aditya L1 mission, you will be able to realize that many of the experiments have been particularly designed to capture the variability of solar wind over the solar cycle. Okay, and it is also useful to describe the solar wind in terms of quantities that are conserved in the plasma flow. So these numbers are flux through a sphere at 1 astronomical unit. Okay, the total amount of mass or number of particles that are going away is shown in this. Okay, so number of protons 8.4 10 to the power of 35 per second. Okay, every second this many number of protons are going away. The total mass that is being carried away is 10 to the power of 12 grams per second. So you put this in comparison to 10 to the power of 30 kg, which is the solar mass. So 10 to the power of 12, although appears to be comparable because 12 and 30 are differing by what, like 18, but more importantly, so the number is so small in comparison to 10 to the power of 30 because every time it is several orders of magnitude larger than the 10 to the power of 12. The radial momentum, kinetic energy, thermal energy, magnetic energy, radial magnetic flux, all these numbers are huge. They are through a sphere of radius 1 astronomical unit. Okay, so solar wind, or the way solar wind escapes the sun's gravity, is a very interesting case, which cannot be understood by simple physics. So, because you are expecting particles with a particular mass, let's say electron, to be accelerated to a velocity by a heat source which is at 5800 Kelvin. Okay, so sun surface is only the heat source, right? So the electrons should get like 280 kilometers per second velocity just by being put at 5800 Kelvin, which doesn't seem to be practical. So the surface of the sun is relatively cool at 5800 Kelvin compared to the solar wind, whose protons have a temperature of 1,20,000 Kelvin. So above the photosphere, the temperature first drops and then increases. And suddenly, about 2000 kilometers or about 0.003 solar radii, the electrons and ions heat rapidly. Okay. So what could these do is very controversial. Alpha waves due to the wiggling of field lines by the photosphere, or release of magnetic energy due to the process known as reconnection, sound waves, or the other. Right. The point is, we can have the solar wind acceleration is a particularly difficult process to explain, considering the fact that if it is only photosphere which is responsible for the heating of solar wind, or for the energization of solar wind. So sun's atmosphere boils off into the space and is accelerated to very large velocities. So many theories were proposed, and Parker's theory in 1958 was a successful one, which proposed that the solar wind was a result of high temperature corona, and Parker developed a hydrodynamic model to support this idea. Based on this, Dessler developed a simple gravitational nozzle which demonstrated the basic physics. We will not go into the details of deriving the Parker's theory, but we can, at this point of time, it is enough for us to understand that solar wind is a fluid which is governed by ideal hydrodynamics, and it can be considered, the simple explanation for solar wind acceleration is a fluid which is escaping towards a very low pressure regions of the solar system. Okay, right. Now, solar wind is can be considered of two types: solar wind type 1 and solar wind type 2. So what is solar wind type 1? Fast solar wind near activity minimum. This characterization, or this categorization, can be mainly based on the velocity or the number of particles. Okay, so fast solar wind can have velocities up to 800 kilometers per second. Okay, it's not kilometers per hour; it's kilometers per second. You know how much is 800 kilometers per second, right? And slow solar wind can be of the order of 400 kilometers per second. And the type 2 solar wind is what you get near solar activity maximum, and solar associated with the can also be type 2 solar wind is what you get near solar wind activity maximum, and is also associated with shocks, and its velocity can go to as high as 2000 kilometers per second. Okay, so this information was something about coronal mass ejections, what are solar flares, basic idea or basic properties of coronal mass ejections of solar flares, and then the most important piece of sun-earth interaction, which is called as the solar wind. Okay, how we know that solar wind is there, etc. So in the subsequent lectures, we will try to understand how solar wind interacts with different planets, and more importantly, when we say geospace, what is geospace? Geospace is something that is surrounding the Earth, which is massively influenced by the sun and its activity. And more importantly, the state of matter which is present in geospace is primarily plasma. So what we will try to understand, we will see how is plasma different from an ideal gas, and we will briefly touch upon concepts of plasma physics which are relevant for understanding sun earth interaction. All right.